Good day, ladies and gentlemen. My name is Michael van Schoor from the CSIR mining cluster, and the title of my talk is Supporting Health, Safety and Optimal Extraction through the use of a geophysical toolbox approach. Just briefly what I will cover in this talk, I will start off with some background and context, leading into a need statement and a proposal for a likely solution. The solution is the geophysical toolbox that's mentioned in the title, and it includes three geophysical methods, namely electrical resistance tomography or ERT, borehole radar, and ground penetrating radar or GPR. I will give you a bit more information about how to apply the geophysical toolbox, and I'll say a few words about the value that this adds to the mining industry, and then of course some conclusions. Okay, let's start with the background and the context. So the local mining industry, specifically the deep level platinum and gold industry, they extract thin tabular ore bodies known as reefs at great depths. And this combination of great depth and ore body geometry makes it a very challenging environment, or makes mining a very challenging exercise. And some of the challenges that I encountered include very confined workspaces, harsh environmental conditions like high temperatures, high humidity, dust, noise, and so on. And also sometimes the roof or the hanging wall, as the mining industry refers to it, have structures in them that make them unstable. And this poses the risk of falls of ground and of course fatalities. In the last decade or so, the mining industry realized the need to embrace the concept of modernization, to adopt certain technologies to make mining easier and more cost effective, because if they don't implement these type of technologies as soon as possible, it will shorten the life or the expected life of the different mines. So this is all with the purpose of extending the life or the longevity of the mining industry, specifically the gold and platinum industries. There are basically two key technology drivers that basically dictate the implementation of technologies. The one is the so-called zero harm objective, and the second one is all about optimal extraction. So in terms of the zero harm objective, we've seen over the last couple of decades that there's been a steady decline in the number of mining fatalities. However, if you look at the last part of that graph on the left, you can see that the trend is now slowly plateauing, which means there's still a lot that can be done to achieve the zero harm objective. If you look at the pie chart on the right, it shows you an interesting fact. If you look at how these fatalities every year is made up, it shows that falls of ground constitute about 40 to 50% of the annual fatalities. And that's what I've referred to earlier, when you have an instability in the roof and you have a rockfall. And this is exactly where some of the geophysical technologies can play a key role. If you look at optimal extraction, the best way to explain this is to look at the value locked up in a block of ground. And the schematic I've got here shows a typical deep level platinum mining example, where they extract again a thin tabular ore body shown in yellow. So if you look at that blue portion, the highlighted blue portion, that denotes a piece of ground that will be extracted over a period of say 3 to 6 months. In this example, it's a 120 by 120 by 1 meter ore body. And if you look at a typical platinum grade of 6 grams per ton, that block equates to a value of about 150 million South African rands. Now, if you have any geological structures that's unseen when they commence with the mining of that block, and it disrupts the continuity of that reef horizon, it could lead to quite significant losses of potential income. Further problem with these type of geological structures is not only do they compromise optimal extraction, but they also compromise safety, because these structures are often associated with poor ground conditions. Okay, so let's look at the need statement and a possible solution. So the mining industry have long realized that if they can implement technologies that allows them to look ahead of mining before they actually mine out the block, and they can identify these hazardous geological structures, it will help them to optimize extraction and to achieve possible zero harm. And the solution that we propose is the application of a geophysical toolbox approach. And the primary geophysical methods in our geophysical toolbox is, as I said earlier, electrical resistivity tomography, Borehole radar, and ground penetrating radar. In the next few slides, I'll cover each of these three technologies briefly. I'll just give a very brief summary of how it works and what it can do for you. Let's start off with the ERT method. So electrical resistance tomography is based on the medical equivalent tomographic imaging approach. In the mining context, what we do is we put a ring of electrodes around a body of interest, in this case that little to-be mined block. So if you look at the schematic bottom left, it shows you how we put, in principle, electrodes all around that block, and if there's any disruption in the flat-lying continuity or natural undisturbed reef horizon, it will show up in your tomograms as a resistivity anomaly. That's just a schematic on the left, but the image on the right shows an actual field survey result from one of the local platinum mines, where we were able to map known slump structures known as potholes in a old abandoned stope. Okay, Borehole radar is basically a radar technology that's deployed in a strategically drilled borehole. So if you look at the top schematic, what has to be done is a borehole is drilled subparallel to the reef or ore body horizon. A radar transmitter is put down the hole and transmits radar energy into the rock mass. A receiver that's co-located with the transmitter receives any reflected signals that's caused by any changes in the dielectric properties of the rock mass. So if you have any change from one rock type to another, or in this case the thin ore body horizon, it will show up as a clear reflection on your radargrams shown there at the bottom right. So due to this very specific geometry of Borehole radar, your output is typically in the form of a 2D cross-sectional radargram. But we have previously shown that if you combine the outputs from multiple boreholes, you can come up with a pseudo 3D visualization of the ore body horizon, as shown there on the left bottom image. And you can then clearly see the lateral extent and depth and so on of these type of slump structures or any similar geological structure that is possibly impeding the extraction of that portion of ore body. Ground penetrating radar it works on the same principle as the Borehole radar. The only difference is that your sensors are, in this case, handheld, and it works at a very much higher frequency than the Borehole radar. This implies that you have a much shorter range, but your mapping accuracy or resolution is much higher. So it's got a very specific purpose that it's used for. It's used to scan the immediate hanging wall or roof of the excavation, to look for any structures that could cause a fall of ground or instability in that hanging wall. As was the case with the Borehole radar, we typically, if you do a single profile, you produce a 2D cross-sectional view, such as the one shown below the image of the guys doing a survey. But again, if you combine a bunch of closely spaced parallel profiles, you can again produce a 3D visualization of that rock mass above you. So let's look at the geophysical toolbox approach. This next slide basically just gives a brief summary or overview of what I was just talking about. So your ERT can be used as a reconnaissance tool because it's got the lowest mapping accuracy or resolution. You can apply it in reconnaissance mode to come up with these plan views of the mining block to show any potential areas where there might be a disruption or geological structure that could impede extraction. You can then use the medium resolution Borehole radar approach or technology to do follow-up work, or to get a cross-sectional view of that structure to see its depth, its lateral extent, whether it affects the reef continuity at all or whether it just displaces the reef, and so on. Finally, you have the high resolution mapping of the GPR technology that allows you to scan the immediate hanging wall to look for those structures that cause a lot of the falls of ground and fatalities in the local mining industry. So this slide is just basically a summary of how you can use all these technologies in an integrated fashion, basically a use case for the mining industry. So if a mine has a to-be-mined block, that's at the top there of the schematic, they can start off, as I said previously, with a reconnaissance approach, look for those structures on the mine plans that, or the areas on the mine plan that might be problematic. They can then move in with a follow-up medium resolution bore radar to get a better handle on the geometry of these structures. At any point, all of this data from the different geophysical methods can be subjected to further analysis, maybe things like data analytics, artificial intelligence, machine learning, to ultimately produce a virtual 3D model of the ore body. And this can then be used to create safety risk maps and to aid in decision support. Just to note that the GPR technology, because it focuses on the immediate hanging wall of all excavations, it is central to any mining operation. So you would apply the GPR method at any point in the development of the excavations, just to make sure that the working environments are safe. Okay, then the obvious question arises: what's the value add for the mining industry? Why would mines want to apply these geophysical methods? What has traditionally been done to get the same information when geophysics wasn't around, or when they choose not to do geophysics? So the short answer is that the traditional alternative is geological diamond drilling or core drilling. The problem with that approach, it's very time consuming, it's relatively expensive, and it provides limited coverage of the reef intersection. So the schematic at the bottom of the slide just illustrates this through a practical example. If you look at the red line that's supposed to be the reef plane, so if you have one single geological diamond borehole that's drilled from a lower level up to the reef horizon, it gives you just a single intersection point on that reef horizon. In contrast, cleverly drilled borehole used for bore radar can provide you with a whole line or basically a profile of reef intersection points. And again, if you combine multiple boreholes, you can even get a 3D picture of that reef horizon in the to-be-mined block. To get the same type of information using individual core drill holes will probably require at least 20 to 30 carefully placed boreholes, which will be very expensive and time consuming. The ideal approach is to actually combine diamond drilling and bore radar, for example, because you still need the odd sample to do assaying on to get grade information and so on. But a more cost-effective approach would be to integrate the two approaches. And finally, a conclusion. Basically, the integrated use of in-mine geophysical technologies, or the geophysical toolbox approach, can provide quantitative information about the ore body or the reef several tens of meters ahead of mining. You can even do this up to several hundred meters ahead of mining if your geometry or your mining layout allows for it. This applies significant potential cost saving, optimizing extraction, while at the same time contributing to the zero harm objective. Thank you very much. We can now take questions.